Welcome to Chapter 10 of Earth History for Finlandia University. With this chapter, we'll be discussing weathering, soil, and erosion, how that interworks with the geology we've discussed in previous chapters to, again, of course, create the world that we all live and breathe in every single day. I am coming down from sickness, so if my voice seems kind of gross, I apologize. That's the reason. Likewise, I might have to take breaks to cough or something like that, just so you are well aware of when that happens. Anyways, beyond that, let's get into Chapter 10. Weathering and erosion. They're words that we use somewhat interchangeably, but they are, in fact, two different processes. Weathering is the process of decomposing a rock into a sediment or breaking it down into bits. When I say sediment, we've talked about that before. That is dirt, that's just sand, that's just soil, stuff like that. We call that sediment. And what that sediment is, where the sediment originates from, is larger full-size rocks and geologic formations that have been essentially crumbled up. Take a cookie, right? Crumble it between your hands. That's the idea we're getting here. Within weathering, we have two distinct processes that decompose the rocks, if you will. We have mechanical or physical processes, and then we have chemical weathering. That usually involves a reaction with air or water to create a product that is different physically and chemically from the source material. Namely, mechanical or physical weathering is the breaking down without some sort of chemical change. We'll discuss both of these in depth. This photo here shows weathering done by the wave energy in central Greece and freshwater percolation downward through the limestone and partial dissolving of it to form caves and holes. So what that means, well, of course, the water is going to strike the waves and it's going to beat on the waves and break chunks off, right? We've all been to beaches. We've seen outcrops at beaches. We've seen this happen. But furthermore, the wave isn't necessarily what's going to make all these nice holes and these cracks and stuff like that, right? That weathering has to do with things other than the wave, such as rainwater falling down. This is a limestone outcrop. Limestone reacts somewhat vigorously to water, creating what we see here. This big inlet here wasn't caused by the randomness of waves necessarily, perhaps something else. And then we'll get into why this crack exists up here too. But take a few moments, think about, look at this picture, all the different effects that happen to create the image that you're seeing before you. They're varied, and they're all every single day. Mechanical weathering. We talked about that before. That is the physical process of decomposing or breaking down the rocks, but not chemically altering them in some way. A few major components we have here include pressure release fracturing. This is when a formerly buried rock is expanded upon recovery. Essentially, the lack of pressure allows the rock to exhale, breathe out, if you will, causing some sort of fracturing. You can also get frost wedging if you're in a location that gets below zero and the water turns into ice crystals like that. What happens when a liquid turns into a solid? It expands. And that expansion and release of freezing and thawing water busts up rock, right? Abrasion, probably the most common weathering you think of, which is simply rocks rolling around, contacting each other, wind, sand dunes, things of those nature. Organic activity like roots, right? Organic activity, roots can break apart rocks. We've all been to a rock outcrop before and saw a tree in the middle, growing in the middle of a rock. Well, take a look at that tree. You're going to notice there's a very thin crevice formed in the rock right around that tree, and that's where the branches are going, right? And lastly, thermal expansion and contraction. This is the essentially what happens while we have potholes in our roads. That same basic phenomenon works in most any rock that can contract and expand given heat. Here we have a large scale explanation of a couple of these processes. You start out with a mountain on the left and you go downriver to the ocean on the right here. What happens with those mountains? Well, you can have weathering, such as rain or wind, loosen some quartz grains from granite. The granite erodes the base feldspars, what have you, erode out of the granite. The quartz, however, is less prone to erosion, less prone to weathering. So the quartz gets removed, weathered out of the granite. The rain and snow melt, erode the quartz grain, and wash it into the stream. Erosion, as we're hinting to here, is more the movement of the material than the breaking of the material. So you have some granite up in the mountain. Over here, rain comes down, wind blows, people walk, animals walk, trees crack the rock. As said before, all of these can work at top of mountain, frost wedging, very significant thing. Essentially crumbling up a granite, which we talked about, igneous rock from chapter 3, and I guess last chapter too. Breaking down that rock into its subsequent minerals. Those minerals are then brought by that rain and snow into this river channel here. The stream transports the quartz grain downslope, continuing down, if the quartz isn't caught by something in the river or the river channel or the topography of the river, what have you. Eventually, said quartz grains are transported to the shoreline where they rework in the surf. What is sand? Sand is predominantly quartz. Quartz is something that doesn't necessarily weather chemically into other things very readily. So that's why we get an abundance of quartz throughout sediments. And then lastly, during a large storm, that quartz grain may be washed out into sea and finally deposited. Fantastic. That is one rock that broke down that happened to have a grain that made this trip. And remember, mountains are full of rocks, right? This stuff happens all day, every day, in very much these similar formats. This is a cool image. This is a half dome at Yosemite National Park in California. What are we looking at here? Why is this standing out so much? More likely than not, this is a laccolith or a batholith, something along those lines from volcanoes chapter or two ago, when we talked about a plutonic magma chamber that cooled before it was able to be released by a volcano. And then over time, what was the mountain on top of it weathered down, the sediment of the mountain weathered down, the composite volcano, the composite weathered down, leaving this this pluton, I should say, to be exposed to the air. What happens when this gets exposed? Well, all the rock and sediment that was on top of this when it was a volcano, that pressure is no longer there. And what if we notice, if we look over here to the left, you can see some sheeting going on. Some almost like the rock is expanding and stretching out. Pressure released fracturing. Here's a closer view of exactly what we're talking about here. This breakage is the result of the rock being confined and no longer having been confined by the release of that pressure, by the erosion and weathering of the stuff that was on top of it, essentially. And that's, and we say it's that way because, well, that's exactly what it looks like, right? This erosion is very top layer, very, movement in those sorts of ways. Frost wedging, I don't think I need to dig into this too much, but frost wedging is when you have water, again, that freezes, thaws, expands out, moves back and forth. That's what happens in our streets all the time. We're always having to get road work done because, especially up in colder weather climates, such as the UP up here, you get the water separating out the materials. Frost wedging, dislodging rocks from cliffs, creating talus slopes. We'll get into talus slopes at the end of this. Consisting of loose angular boulders, etc., right? This is a mechanical process. You're just breaking up the bedrock into chunks and having it fall down. That's why you have, on large mountains a lot of the time, these piles of debris and sediment on the bottom of them. They were busted out by ice. Wave energy, of course, along shorelines and lakes can rapidly abrade and round rocks such as these. You go to a lot of beaches, you're going to find the rocks are somewhat rounded, somewhat smooth, right? A skipping stone is very smooth and flat. That's because of the slow, gradual, general process of the water running back and forth over the rocks, the sand being carried by the water, slowly grinding down the rocks. The rocks aren't moving usually because the water's somewhat calm, landing in these nice, soft, rounded surfaces. Essentially, you're taking a really fine sandpaper and slowly moving it back and forth over the rocks, you know, a couple times a minute every day for as long as those rocks have been on that beach. They get nice and rounded. Eventually, they get so rounded they just completely collapse. And as you sand it, you take off parts of the rock, adding to the sandpaper, quote unquote, of the beach. Of course, water is one mechanical process, wind is another, as shown here. Uh, Deserts, dunes, right? Picture a desert, you're probably picturing rolling big old dust bowls and clouds of dust, stuff like that. Exact same process. Here you have some of that biological fracture I talked about here. And this again, when you're out hiking around, you come across a rock outcrop and it's a tree, take a couple extra moments and try to find the branches of that tree. You can be very impressed at the ingenuity, if you will, of that tree to locate any sources where it can soak up water. It is truly impressive. And it doesn't take a lot of tree to really break a big chunk of rock off. It's definitely an interesting thing to think about, right? Cool. Mechanical processes, essentially punching the rock into pieces. But mechanical is one part. We also need to discuss chemical process. Dissolution, hydrolysis, and oxidation, all very common forms of chemical weathering. What a lot of time happens when you have chemical processes, such as water interacting with a particular, this is a salt here, NaCl, and looks to be a 1-to-1 configuration, or actually maybe a 2-to-1. Yeah, 2-to-1 configuration. What you have here is the process where the water molecules come into the matrix, come into the crystalline, the atomic structure of the rock, and interact with what we're talking about here. These cations, sodium cations, really want to play with the water. And the chlorine anions also really want to play with the water on its opposite side, right? The little Mickey Mouse shape of water, the two positive hydrogens, the one negative oxygen anion. So what you have here is the water is the more attractive mate for the sodium and the chlorine. So they break off into their subsequent parts and at an atomic level break down the salt we're talking about here. This process happens at atomic level, and that atomic level happens throughout the crystal, throughout the rock, throughout the boulder that you're talking about. These caverns here are formed when groundwater dissolved the limestone. Not exactly this process, because limestone is NaCl, but a very similar process happens at this atomic level. That's where the cave gets flushed out. After the cave is flushed out, these stalactites, stalagmites, and columns, columnar builds here, as shown here in this grotto in France, formed through reprecipitation of limestone from the groundwater saturated from the calcium carbonate. If you've ever been on a tour in a limestone cave before, they'll tell you about this process. The water dripping down, bringing down the sediments that slowly form to make these nice little stalactites and stalagmites that we find available. So this was a kind of a two-step process, you could argue, of the cave being formed and the stalactites and stalagmites growing as a result of the cave being formed. They are separate but equal, I guess you could sort of say. Yeah. Other chemical weathering processes include salt cracking, exfoliation, spheroidal weathering. Other processes that come about through this weathering include salt cracking, exfoliation, spheroidal weathering. Salt cracking is when salt chemically precipitates the rocks, and then the growing salt crystals push the rocks apart, right? Salt very much interacts. Salt, as said, shown right here, the cation very much interacts with at the molecular level with whatever you happen to be dealing with at the moment. And then the salt crystals form, the halite crystal, what have you, forms, and that formation of the crystal therefore further alters the rock. Salt's the common one we can talk about here, but this kind of process works with most any mineral that has the ability to grow, but only will grow in a certain fashion, right? Exfoliation happens. For example, granite sheets peel off due to hydrolysis expansion, essentially clay formation and swelling. We'll go into some pictures about this, but that kind of is this process here, right? The release of pressure, the allowance of new minerals to form in the cracks of those, thereby increasing the size of the crack, etc., etc. And of course, spheroidal weathering, turning something into a ball, a sphere, right? Here we have a very cool image. This is crystallized salt that has loosened up sand grains in the sandstone to form depressions in Montana. As you can see, these are kind of small depressions, right? How can these things be formed? Well, this is formed by a certain mineral eroding out and causing weathering and eroding out, causing a breakup of the sand, but only in certain locations. These aren't necessarily dug out. I mean, that rock there is, that hammer is being held. This is a vertical picture you're looking at here, bottom to top. This wasn't made by, let's say, a drill, or it's not a spooky face appearing in the rocks down here. What it is the process of, say, a salt disrupting at atomic level the makeup of the sandstone, the different minerals composited in the sandstone, and then it takes the various minerals involved and it moves them, slowly builds them around, dishes them out, brings new stuff in, etc., etc. And what you end up getting is these nice, round, spheroidal looking shapes in them. They're simultaneously random and not. You're not going to get pyramids growing here. You're always going to get these sort of polygon, roundish looking shapes. But again, they're not all perfectly round, right? That's more trapezoidal, it's just with rounded edges. So it's interesting, the randomness involved in this process and the strict rules at which it also simultaneously follows. Here's a bit more about the exfoliation we talked about earlier, right? Here I told you that granitic pluton, that unused magma from a volcanic activity, has a bunch of sediment placed on it. Over time, that sediment erodes away, and the granite, or possibly the granite, is uplifted as a result, right? Due to tectonic forces. And as that granite uplifts, it's able essentially to breathe, let out the pressure, expand a bit. Once it expands a bit here, all those expansions, water can come in, bring in different minerals, create clays in between them, what have you, and yeah, sheet out essentially. Very common in granite because, again, granite is your crust, continental crust rock. So you're going to have lots of granite everywhere you have continental crust, and likewise you're going to have, due to weathering, these sort of events happen. It's a combination of various weathering and eroding factors. Weathering breaking the rock up, erosion bringing minerals in to further break up the rock by the formation of, as I said at the beginning, clays and what have you. And I talked about this already with the beach, spheroidal weathering. Here we have some diabase that has been eroded out at Gettysburg, right? It's round because, again, you can imagine the sediment essentially working like a very slow sandpaper. It keeps hitting it slowly, but it's not hitting it strong enough to break off large pieces. It's just hitting it enough to round a corner. If you want to sand a nice smooth edge in something, you just slowly work it over time, right? If you want a sharp edge, you need to pull out the Dremel and do some cutting. That's the difference we're talking about here. So there you go. There's a brief of mechanical and chemical weathering. As I always say in these videos, this conversation is much more in depth than what I'm simply describing here. My suggestion to you, if you're like, I wonder how XYZ commented, let me see those comments. I can lead you in a direction that hopefully fulfills the question you are asking. But what I want out of this class, I've told you guys this many times, I want next time you go out on a walk, you notice some of this stuff, stop and think about how it got there. You're going to find nature so much more interesting if you know a little bit about what you're looking at. Besides, oh, cool rock. Oh, hey, it's got some that tree cut down some fracturing and the roots are literally pulling that rock apart. That's pretty boss, right? That's the idea we're going with here. Cool. We talked about how to make sediment via chemical and mechanical weathering and erosion. Now let's talk about what happens to them afterwards. What is soil? Soil is composed of many different layers. We can start by talking about regolith. This is the surface layer of loose rock. But loose rock doesn't necessarily make a soil. It is, but you don't want to grow. Stuff doesn't like to grow in just loose rock, right? Otherwise, sandy beaches would be covered in trees. So, to make a soil, you need to include a couple of different things. You include mineral grains, such as clay, silt, sand, rock fragments, the dirt of the soil, but you also include some organic matter, dead leaves, animal carcasses, bug carcasses, stuff like that. And finally, usually you want the soil to be somewhat moist. These three components are necessary for soil to do its job, right? If you're missing organic matter, well, then you probably have beach sand. If you're missing water and gas, well, your soil's dry and hard and nothing to grow in it. You're missing the minerals, you probably got some, wet cow poop, I guess? It's not soil, right? We tend to call the organic debris litter, and we tend to call the decomposed litter, the stuff that's actually useful, humus. Within soil, I got a image here to further explain this. We have many different what we call horizons, or sort of definitive layers of soil that are distinct from each other. You can always start at the top with the O horizon, the topmost part of the soil. This is the stuff that the grass roots are in. It is technically different, but more or less it is contiguous with the A horizon, which is your mixture of humus, silt, sand, and clay that make up your topsoil. You go to Walmart, you build in a garden, you go to Walmart, you buy a bag of topsoil. You're buying essentially A horizon soil. This is what plants love. This is where, again, as you look here, you get most of your humus, which is your decomposed litter. You have your organics for your nutrients. Your water is held very well at this stage, and that's what plants like. Below, as we leave the A horizon, we start to run out of the organic components, and that's where we enter what's called the B horizon, your subsoil. Trees can get this deep, they'll be fine, but plants don't, because you run out of nutrients at that point. You're not having the wealth of variety of water and dead bugs and dead trees and stuff like that to provide you with the sustenance you need for plants to live. Once you get beyond that, you can drop into what's called the C horizon, which is essentially getting more into bedrock than soil at that point. Water, of course, falls through the soil, and water is mostly held in the O and the A, which then absorbed and used, but it can fall through to the B, and then the C eventually is leading yourself to groundwater at that point. Here's some images explaining what I was talking about. Here we have a cartoon on the left. Here we have an actual picture on the right, crazy as it is. And again, your topsoil is the stuff, your black soil, all the roots are held there. It's what you actually want and care about. Your topsoil is your good stuff, right? If you don't have very good topsoil, you probably have a lot more so subsoil, B horizon, wherein it is essentially like a lesser version of A. Water doesn't get down there as much, organics don't get down there as much, these issues. All this actual sediment, as shown here, O, A, and B, all sit on top of weathered bedrock, C, down here. This is a loose material, loose rock. Water can still cut through it, but you've essentially lost all of your humus. You've lost all of your organic component, and you essentially are just, the C horizon is more so the beat up bedrock than it is anything having to do with soil, if that makes sense. And you can usually tell by color, right? Look at this image here. Your A horizon is your nice black dirt that you want to grow your plants. And as you go from B to C, you lighten up that amount because you're losing your organics, you're losing your waters, etc., etc. C, there may be an equal clay amount between A, B, and C, but the clay is not the thing you care about. You got a very clay heavy soil, but if you also happen to have a good built up soil of nutrients, things can still work in your way, although you don't want clay heavy soil. It's more of a gardening thing than a geology thing at this point. So again, 4 major horizons. A, B, and C are technically your major horizons, but you can consider O to be a horizon as well if you want. This does subcut more so than what I'm discussing here. D and E are also horizons that you can talk about. But for sake of conversation, topsoil, subsoil, not soil, essentially. Cool. Those are the basic horizons of soil. Let's talk about classifications. We can talk about soil order, perhaps, which is the hierarchy level of soil classification based on the physical and chemical characteristics, thickness, and the color of the horizons. The soil series, in contrast, to be a low-level classification of the soils that you're talking about. And they're based on soil location, essentially. Your soil order is what the soil is. Soil series is, as said here, named based on mapping. How does soil form? Soil forms usually from a parent rock, right? As we said, all sediments come from some original source material. What that source material is dictates what the soil that you have. And same thing with a beach. You get sandy beaches from certain source materials and phoneticness of water, and then you get rocky beaches from different source materials and phoneticness of water. For example, if you have a or down here, we could talk about our climate, and we could say very salt-crusted soil. You got a lot of halides going on, lots of halogens in the environment. You're going to get a certain type of soil. Petrocal. I'm not super up on my soils. I apologize. You get calcite forming a soil. Caliche, I'm going to assume. I'm not going to dwell too much on soils. It's not my forte. But the type of soil the type of source rock that you have, type of parent rock you have, dictates the type of soil you get. There is a very good reason why some places can grow a lot of crops, other places cannot. That is due mostly to the mineral grains, clays, sands, silts, rock fragments, what have you, that allow the organic material in the water to be collected. As I said before, you can grow stuff in heavy clay soil. You don't really want to, though. Clay doesn't hold the organics in the water nearly as well as a nice silty, a nice shaly soil. And again, sand, as said before here, right? You don't grow crops a lot on sand. That's not good, rich topsoil. And that all is directly related to the surrounding bedrock, surrounding source rock, and the processes that weathered and eroded those down from rock to sediment, and then sediment to soil. Down here, you have, if you really want to learn more about this and you have the book handy, you can go look that up. That being said, there's lots of good information on soils, especially from a non-geology perspective. If you're interested more in the gardening aspects of this, lots of good information out there on importance of soil. There's a lot of different bags of soil at Walmart for a reason. I'll put it that way. And they're not all built the same. So how do you affect those various components of soil? Well, the rate of plant growth and decay affects it a lot. Right? If you want dead stuff in your ground, you'd have dead stuff there, but you also don't want the dead stuff to be chewed up so badly all the nutrients are soaked up by the surrounding bacteria. None of those nutrients actually get down in the soil. Slope and steepness plays a huge factor. You tend not to see gardens on the sides of steep mountains and cliffs because the steepness drops the soil off of the edge, right? It's gravity. It's how that works. Time is an important factor here. Chemical weather is usually slow. You don't build a soil during one cycle. If you want to plant a garden, don't expect your first and second years to be as profitable in that soil as your 7th and 8th years. Farms need to grow. The humus needs to be developed. Again, this is more of a gardening conversation and geology conversation, but these all tie in very well together. And of course, soil transport. What's bringing your soil here? What's taking your soil away? Right? There is a very important reason why the civilizations of the world all started near rivers, because rivers provide you with not only access to water, but the best, most fertile growing soil. Why do you think that is? How could actively flowing rivers allow for the most fertile land, the best topsoil? Why do you think that is? Again, look at your components of soil, how you make a soil, and that might provide you with some clues. Cool. Yeah, let's take a look at this image here, right? It kind of, you don't maybe think about it at first glance, but pay close attention here. Notice how one side of all these hills has trees and the other side doesn't. Interesting, right? What could that mean? Why do you think trees only really prefer to grow on one side of this and not the other? Well, take a second, pause here. Hold up, there you go. Pause here. Take 5 minutes, just try to figure out why you think that is. Consider slope, time, soil transportation, soil classification order, what your horizons look like. Trees and grass are very different root characteristics, right? Root profiles. Could this all play a factor? Cool. That was soil. Let's talk a bit more about the erosion side of things. Mass wasting and landslides. What is mass wasting? Well, mass wasting is the downward slope due to gravity, downward movement due to gravity. Something going down the hill is mass wasting. Could be big, could be small. We all regard that as mass wasting. You probably don't know it as landslides. They're the exact same thing, just one's more sciencey. And these are directly the result of downward creep, gradual downhill movement, freeze thaw cycles pushing things around. Mass wasting takes time. As shown here, a good evidence of mass wasting of the slow creep, the slow crawl of soil, is curved tree trunks. I'm sure you've seen on slight hills trees that have been bending up. That's because they started, when those trees started growing, they were more or less vertical. But the ground that they're in has been slowly sliding down, causing the tree to have to readjust and continue trying to grow vertically. What better evidence do you need of this stuff happening? Telephone poles, of course, be another concept, a newer concept, depending on the speed at which this landslide is moving, and collapsing road cuts. If you ever travel like to the Appalachians, you're going to see road cuts having to constantly be repaired and updated because the ground is slowly moving and wasting over time. Different types of mass wasting. Well, let's talk about the flow. What is flow? Flow is the loose sediment that moves downslope in a slurry-like fluid. This is a slow or a fast process. If it's slow, we call it creep, the loose material moving very slowly. If it's moving somewhat faster than creeping, we call it an earth flow. And if it's moving kind of fast, we call it a mud flow. If I say mud flow, you know what I mean, right? But just because you don't have a visual classic landslide happening doesn't mean hills and mountains and things along those lines are not slowly falling down. The soil's tilted a certain way. It doesn't want to naturally stay at some awkward angle. Gravity pulls everything flat, right? Here you have some examples of creep. Essentially, just, again, it's the slow fall of things that are at angles. Things don't like to be sideways. They like to be flat. Happens in many different ways. Rock slides, debris and mud flows, trees moving positions, rocks falling off the edge of cliffs, have you, all mass wasting examples. If you'd like to know if this concept is eluding you, please comment. I can hopefully direct you towards better information. Exactly what I said here, right? Do you think when this tree started growing, it was growing at this oblique angle and then decided at some point in its life to turn up? No, of course not. This tree's on the side of a hill, and when this tree first started, it was vertical. But the hill's been moving downward such that the tree has been sliding, the tree and the roots have been sliding down slowly, creeping on down, and the tree had to adjust as it grew. Right? Slide. What is slide? Well, it's exactly what it sounds like, large blocks moving downward. You can have slumps, which are shown here, which is large blocks of sediment and soil and ground rock and source material all moving as one large component. You have rock slides where instead of moving as one large component, they separate. And again, these images show a good example of the difference between the two. Notice the slump rock has vegetation in it. The trees are essentially holding the material in place. The rock slide, no vegetation. The material can break off as it needs to. Why do slides, flows, and falls occur? Primary motivating factor be the steepness of the slope. You got a steep slope. Soil, rock, trees, what have you, don't like to be on steep slopes, so they're going to eventually fall and subside down. Type of rock, orientation of rock layers is very vital to this conversation, as we're going to show here in a little bit. But a very strong rock is going to be resistant to gravity. Rock layers that are horizontal in nature can be very resistant to slipping and sliding around. The unconsolidated material around it. If your soil is loose, you don't have trees binding the material together, you don't have roots holding stuff together, you're more likely to slip and fall. Water and vegetation, exactly this process I was talking about. Water there, the idea being how moist the soil is. The more moist the soil is, maybe the more likely it's going to want to move, right? You're going to have mass wasting after rain a lot more than you have mass wasting after droughts. And lastly, earthquakes and volcanoes. If nature decides to get really mad and shake and blow its gasket all over the place, yeah, you're going to cause some damage to the earth. These examples are what I was referring to. Notice here, you have weak shale layers as opposed to stronger igneous layer, we'll call it, this blue guy here, the sandstone. These weak shale layers don't mind sliding down this hill due to gravity. So if you try to build a retaining wall, that retaining wall is going to run into the issue of the shale not being strong enough on its own to hold its position. But, and again, the organization of this wants to go downhill. But if the layers are, for example, rotated up in this manner via tectonic activity, then all of a sudden you have a situation where this sandstone, for example, that's stronger than the shale, doesn't really want to fall downhill necessarily because it's being butted up by this very strong granite or whatever that blue rock is. So this isn't going to want to move because gravity wants it to go downward into itself more so than down the hill. So your retaining wall is supported by the outlying geology of the area, thereby creating, lucky for you, a well-supported structure. Angle of repose. Angle of repose essentially is what the material can hold on its own. If you defeat angle of repose, you have mass wasting, you have a landslide. As honestly best shown here, this is probably a better example. You've all built sand castles at the beach before, right? You can only build them so tall. You can only build them at such a certain angle. You build your sand castle too tall, it can't hold its own weight, it collapses down, right? That's angle of repose. It changes depending on structure we're talking about here. This rock talus can hold a better angle of repose because, well, the rock is less likely to move in on itself. Sand, this dry sand here has a smaller angle of repose. Sand's more likely to tumble down on top of itself. If you've ever been to some dunes at a beach before, you're going to notice the dunes slowly moving back and the grass component. You're going to a lot of times find dune here, then at the very top here, big grass component and roots falling out of the sand, beating the angle of repose, essentially. Yeah, and that is weathering and erosion. Pretty straightforward concept, I imagine. The interesting parts that you should note are exactly how mass wasting happens and the slow, gradual development of it is pretty interesting because, again, this tree did not put roots in this particular GPS lat long location, right? And the evidence of that is the fact that this tree's had to adjust its growth pattern to compensate for the hill slowly moving, slowly slumping down. Cool, right? Next time you go outside in the woods, you notice the trees with bent, curved tree trunks. That's telling you things have been moving and changing since the growth of that tree. Other interesting facts, just exactly how soil works, something to keep in mind. Your different horizons, why topsoil is topsoil. Learning about, again, this is more of a gardening and geology aspect, but still interesting. Learning about what makes a good topsoil, how you build topsoil, stuff like that. That's well worth your time and understanding. And furthermore, all the different varied miraculous ways, if you will, that weather and erosion affect the look and feel and change of our planet. Right? Giant granitic plutons shaving off, sheeting off like this, creating these large, thin sheets at the top here due to kind of nothing more than just not having soil on top of them and weather kind of getting in the way of things. Limestone caves, the chemistry behind all this stuff, the actual breaking of the atomic bonds going on in this process. These scarps here, right? This rock that's left standing is probably igneous and harder, less likely to erode than its surrounding material. This, what we're looking at here, this was once all covered by soil because this is probably all the insides of a volcano. This stuff just never happened to leave the volcano. The volcano went dormant. The rock cooled to create whatever you have here, a diorite or whatever. And then the surrounding volcano, the surrounding mountain, essentially, over time eroded away. As it eroded away, it got to the point where sand started doing the erosion instead of water, what sending lots of particles, right? All these particles here coming through here, beating up this rock. Lots of particles move pretty fast, coarse sandpaper, right? This guy, the water is shallow, slowly moving back and forth. A nice soft sandpaper around these rocks. Very angular, very jagged, very smooth and relaxing. Probably because this is angular and jagged, and what happened to it? This is your heavy metal erosion. And this is your soft, singer songwriter James Taylor sort of erosion. Right? Metallica, James Taylor. But this stuff is literally everywhere, right? One of the big factors I want you to take with this class is the geology always has a cool, interesting, exciting story to tell. Next time you take a walk outside, whatever that is, right? Next time you take that walk outside, if you see something that's cool, stop and try to figure out why it's cool. There's a huge story involved in every one of those conversations. So that concludes the end of this presentation. Not too long of one. I'm trying to keep these down to a video, a chapter. I think that would work best. If you have any questions, please leave the comments below. Shoot me an email. Contact me on whatever learning media surface that we're using, Moodle, Canvas, Blackboard, whatever, PowerSchool, I don't know. And yeah, stay safe out there.